Alright, welcome guys to another episode of this tutorial video. Yes, today we'll be looking at the second law of thermodynamics. After a lot of topics, we treated the first law of thermodynamics in the other video, and the processes, the non-flow process, the steady flow process, and all. So today we'll be looking at the second law of thermodynamics. So as you can see on the screen, we have the diagram of a system and its surrounding. Okay, so here is the system and this is the surrounding. Also, you can call it the source of heat, and also this is the sink where it goes. So before we go into that, remember when we were dealing with the first law, when we treated the first law, which says that network cannot be produced, work can never be produced during a cycle without applying heat or without the addition of heat. It's so practical. A system cannot work without gaining heat. It's just like a motorcycle or a car cannot move without fuel. So it's practically impossible to have a car that works with a petrol engine or a diesel engine, and without pouring gasoline or diesel, as the case may be, having it running on the wrong way is not possible. It's not possible. So that is what the first law is trying to insinuate. So that applies here too in the second law. Now the second law is trying to express the fact that the heat now given to the system is not completely used. So some of the heat are being rejected, or are being sent to the sink. So that goes down to the definition proper. So how does this sound? Let's define it properly. Now, the second law of thermodynamics states that it's practically impossible to construct a system that will do no other than operate in a cycle, extract heat from a single reservoir, and then do an equivalent amount of work on the surrounding. That makes sense. So it's just like saying a perpetual motion machine which will receive heat without working. You cannot eat food without doing something that will burn up the energy. You get fat, and probably due to fatigue you may have or fall sick, or as the case may be. So you have to work as you eat. So that is what this is trying to imply. So it's practically impossible to have efficiency 100% because heat must have been lost to the sink. So efficiency hereby is not 100% efficient in summary. So that is what the second law of thermodynamics states. So having said that, we go back to the diagram on the screen. Now, for a heat engine, what is a heat engine? A heat engine is a system which operates continuously and across which its boundary flows only heat and work, nothing else. So as you can see there, heat flowing from a hot body Q1 is supplied to the heat engine, and the heat engine does work with the heat, which is Q1 minus Q2, but it doesn't use up the heat completely, so it rejects some heat to the cold body. So at this point Q2 will be introduced, Q2, Q1. So that's what this diagram means. So the source is the hot body and the sink is the cold body. Generates heat generated from the hot body transferred to the heat engine, does work with it, and then dumps or sends some parts of the energy down to the sink, and vice versa, since energy can neither be created nor destroyed. Now, hence we can say that network done where we are using the magnitude sign means that energy can come from the source and also from the sink, vice versa, so it can be a negative value. So the modulus of heat supplied or heat loss should be a positive value. So thermal efficiency is given by network, which is Q1 minus Q2 over Q1, where Q1 is heat supplied, where Q1 is the heat supplied, and Q2 is the heat rejected. That is for the heat engine, because it's vice versa, or is the other way around for the heat pump. Okay, so for a heat engine, so for a heat engine, so a heat pump now is the inverse of that of a heat engine. How do I mean by this? Now, energy or heat is supplied to the heat pump from a cold body. So heat is extracted from the cold body to the heat pump, and then it goes down to the hot body. So here still remains the source of heat, here remains the sink. So heat is forcefully taken from the cold body, which moves the heat pump and down to the hot body, but this is practically impossible, as the case may be. But a heat pump reacts in diverse ways, so it's practically possible to have it this way, since heat can be channeled back to the hot body. So the heat that is channeled back to the cold body is extracted back again to the hot body, so that keeps it in a circle. That's why you call it a cycle. It's a cycle, not really a cycle. That's why it's a cycle. And just like I said, it's practically impossible to construct a system that will just extract the heat, operate in a cycle, and do exactly an equivalent work on the surrounding without losing some heat. It's not possible. It has to lose some heat. So having said this, let's take a good look at an example that will help us understand this perfectly. So, example 1. A system undergoes a power cycle, receiving, are you there? Receiving 1000 kilojoules by heat transfer from hot combustion gases at a temperature of 500 Kelvin, discharging 600 kilojoules by heat transfer to the atmosphere at 300 Kelvin. Taking the combustion gas and atmosphere as hot and cold bodies respectively, determines for the cycle the network developed and the cycle thermal efficiency. So first of all, you start by writing solution. After that, you draw out, you plot the diagram to illustrate what we mean by that. So I will have this over here, I will have this over here, and I also have this over here. Right. Okay. Okay. The work of art. No. Should learn how to draw sometimes. Helps. Yes. So now they said, remember, here is our hot body, and this is our cold body at temperature 1 500 Kelvin, temperature 2 300 Kelvin. Now the hot body is the combustion gases, okay. This is our heat engine. A power cycle is a heat engine is an example of a power cycle. So heat engine Q1 Q2 respectively, the atmosphere, which is our cold body. Okay, now finally the network, which is Q1 minus Q2 as it implies. So they said the power cycle receives 1000 kilojoules. What does that mean? It means Q1 is supplied to the heat engine is plus 1000 kilojoules. Now discharging 600 means it rejects, that is Q2 minus 600 kilojoules. Now the network obviously will be sorry for that big handwriting. The network, which is Q1 minus Q2, will be the magnitude of Q2 is 600, so network will be 1000 minus 600. So we have that network is 400 kilojoules. Okay, now the cycle thermal efficiency is given by network all over heat supplied. Okay, you know what our network is, we know what our heat supply is. So imputing the values, we have this times 100. So efficiency is what? 40%. Okay. Similarly, we can also say that we can also use the temperatures. Remember, we can also use the temperatures, and similarly this can be 1 minus T2 over T1 times 100%. So 1 minus T2 is what? 300. T1 is 500. Okay, times 100%. So we have that 1 minus 0.6 times 100%. So this is at 0.4 times 100%. Sorry, this is 100. So we clean it over here. %. Okay. So that will give us 40%, which is same as before. Okay, which is the same as the previous answer. So this is an example to help illustrate what we actually meant by the diagram we drew in the first page here at our layer 1. Okay, we have gotten the thermal efficiency just as stated in the question, our network. Alright, everything has been solved. So here comes the end of today's tutorial. I hope you understood every bit. Make sure you stay tuned for more videos, and have a nice day. Thank you.
A little liquor on some ladies, yeah. We did turn up on a daily. It's how I walk up, yeah. Soft walk.